You probably learned a specific story about oil in school. The idea is that it comes from dinosaurs, massive, ancient reptiles perfectly preserved underground, slowly turning into the fuel we use today. It sounds logical enough. Giant animals lead to giant fuel reserves. But if you actually run the numbers, you run into a massive math problem. Even if every single dinosaur that ever lived was completely converted into crude oil, their total combined mass wouldn't even come close to explaining the amount of oil we've pumped out of the ground, let alone the reserves we still have left. To find the real source, look past the giants and focus on something nearly invisible. Our oil comes from unimaginable quantities of microscopic marine organisms, plankton, algae, and bacteria. Trillions upon trillions of these creatures thrived in ancient shallow seas, constantly living, dying, and drifting to the seafloor in a continuous marine snow. Scale, rather than individual size, is the true engine of fossil fuels. It took hundreds of millions of years of microscopic deaths, accumulating layer by layer, to build the concentrated energy reserves that power the modern world. Hundreds of millions of years ago, vast shallow seas covered huge portions of the Earth. Places now completely dry land, across Europe, Africa, Australia, and the Americas, were entirely underwater, teeming with marine life. But look at where our modern reserves sit today. Despite ancient oceans covering the globe, conventional oil is wildly concentrated in a few specific pockets. A single country, Venezuela, holds over 300 billion barrels in its Orinoco Belt alone. Zoom out slightly, and countries surrounding the Arabian Peninsula, Saudi Arabia, Iraq, Iran, and the UAE control a massive share of the world's remaining crude. This creates a geological puzzle. The biological ingredients for oil were present almost everywhere on Earth. Yet only a handful of specific locations managed to convert ancient ocean life into liquid wealth. To understand why oil is so rare, we have to look at the strict gauntlet of conditions required to make it. The first requirement is anoxia. When that plankton died and sank, it had to land on a heavily oxygen-starved seafloor. Without oxygen, bacteria couldn't rot the matter, allowing it to stay perfectly preserved in the mud. Sediment continuously piled on top, driving that organic layer deep into the crust. Here, the geothermal gradient causes temperatures to rise. It must hit an exact zone, between 60 and 120 degrees Celsius, where the rock finally cracks the organic material into liquid oil. The margins here are brutally tight. If the rock stays too shallow and cool, the material remains kerogen, a useless waxy solid. If tectonic forces push it too deep, the extreme heat completely destroys the oil or bakes it down into natural gas. Creating liquid crude requires a rare, mathematically improbable equilibrium, the perfect depth, the exact temperature, and millions of years. That strict alignment immediately disqualifies the vast majority of the Earth's ancient seabeds. Even if a region survives that strict gauntlet, the newly formed liquid oil immediately tries to escape from the pressure. Because crude is lighter than the salty groundwater surrounding it, buoyancy forces it to squeeze upward, migrating toward the surface through tiny pores and fractures. Left unchecked, it will reach the surface and vanish. To capture it, the geology must provide a trap and a seal. The oil travels upward until it hits an impermeable layer of rock, like thick shale or salt. Below that seal, the rock layer must be folded upward into a structural dome, forcing the oil to pool together into a massive reservoir. Winning this geological lottery dictates where oil is found, but the biological variables in the ground dictate its economic value. Among the few regions that hold oil, the physical quality of the crude varies wildly. In Saudi Arabia, much of the crude is sweet and light. It flows easily, has low sulfur, and is highly efficient to refine into gasoline. But in Venezuela's massive reserves, underground microbes actually ate the lighter parts of the oil over millions of years. What remains is a heavy, high-sulfur crude that behaves more like thick tar. These extreme differences in quality dictate entirely separate economic realities. Processing Venezuela's thick crude requires heavily specialized, multi-billion-dollar refining infrastructure, heavily influencing the global supply chains we see today. For decades, there was a competing idea about where all this oil came from. In the 1950s, a theory emerged in the Soviet Union suggesting that oil might not come from life at all. This abiogenic theory proposed that extreme heat and pressure deep inside the Earth's mantle continuously forge hydrocarbons, which then slowly leak up toward the surface. The stakes of this idea are enormous. If oil forms continuously from deep geological pressure alone, then fossil fuels are infinitely renewable. We would expect to find giant oil fields essentially everywhere on Earth, even inside dense, hard basement rocks hundreds of miles away from any ancient ocean. But the oil itself provides chemical forensics that disprove this. This side-by-side diagram compares two molecular structures. On the left is a molecule from a living marine algae cell. On the right is a complex compound found inside crude oil, known as a biomarker. Their shapes are an exact structural match. No known process in the deep Earth can spontaneously forge these highly specific, life-based chemical fossils. And if we overlay a chart of carbon isotope ratios onto this diagram, we see the secondary proof. Living organisms strongly prefer to consume the lighter carbon-12 isotope for their biology. The chart shows that crude oil possesses the exact same unnatural, heavy concentration of carbon-12 found in ancient marine life. The specific sedimentary rock layers, the presence of matching biological markers, and the heavy spikes of carbon-12 all point to a single reality. Oil is a highly specific, strictly non-renewable chemical fossil. The map of modern geopolitical power isn't random. It is entirely dictated by exactly where microscopic marine life happened to fall, get trapped, and slowly cook millions of years before humans ever existed.